Morning, all strong people. Morning session, last day, final day of the conference. Welcome. My name is Mikas Vengris, one of the local gang here at Vilnius University. And it's a pleasure for me to introduce our keynote speaker of today, Fedor Jelezko, who comes to us from the city where Einstein was born, Ulm. And, well, apparently quantum optics is still has a strong vibe in the city. If you think that Fedor is tall, big, you should look at his publication list. And with no further ado, Fedor, you have the floor.
Well, thank you very much for the kind introduction, and it's a pleasure for me to be here, and it's a really exciting conference. I also would like to thank all the organizer team and European Physical Society for the support of this meeting, which is very important. This meeting brings together students from natural sciences all over Europe, and I think this kind of multidisciplinary wide area program is really, I think, important for young scientists. So today I would like to talk about quantum sensing using defects in diamond. So what you see here is a synthetic diamond that is going to be placed in a kind of a holder where we control individual dopants atoms in this diamond using optical and microwave and create coherent states of the dopants that will be used for sensing minute magnetic fields. So why the sensing is so important? So why we think that physics should contribute to sensing, develop new tools for making better sensors? Well, actually, sensing and imaging is a success story where physics contributed to society in the past. Starting from light microscopy, going to the method for structure determination of molecules, for example, electron microscopy or X-ray. These all techniques that have been developed by physicists became a very essential tool in life sciences and medicine, and our life today couldn't be, we couldn't imagine it without basically having this tool at hands. Understanding structure of molecules, understanding structure of materials, understanding properties of materials is all based on development of sensing and imaging technique. And many of these techniques that have been developed in the past are based on a law of a classical physics, like, for example, light microscopy. 20th century is a century of rise of quantum physics, and so the topic today will be about use of quantum technology, control of the quantum states of matter and light for making better sensors. Actually, quantum sensing and metrology is a very wide field, and I wouldn't be able to cover all the area where sensors or new imaging techniques are applied nowadays. I will concentrate more on the work of our team at Ulm University. In Ulm, we are particularly focused on application of quantum sensing for biosciences. And to introduce this goal, so I would like to maybe show you like a dream microscope, I think, for many biologists or biophysicists. This microscope should be able to image complex biomolecules like proteins or DNA and do it in a way that the structure that you get give you access to function. And so function of protein is given by its dynamics. Often it's also promote chemical reactions. So you have to understand the structure of such a molecule in very details. And the microscope you would like to have as a dream should have a sensitivity up to a single atoms to be able to image this complex molecule have a high, of course, spatial resolution for this, but also to image the dynamics, it should provide good enough temporal resolution to see the motion of the protein. And last but not least, so this microscope should be able to operate in a biological environment, perhaps in a living cells. And that's what conventional techniques are usually lacking. Electron microscopy, especially cryo-electron microscopy, rise during last decade, but that operates in vacuum under cryogenic condition. X-ray usually require growing large crystals out of biomolecules, and not all the protein keep its function when being crystallized. Particularly membrane proteins are hard to crystallize. So at the moment, there is no really tools to make such a structure reconstruction possible. And development of these tools is an important field of research, and physicists, we think, can contribute to this by creating new approaches. And so this task is very, very difficult. So today, lecture will be showing you just first steps towards approaching this task. So the two techniques, however, kind of are on a way, or were contributing to this field, resolve structure and dynamics of single molecules, and I present them in a kind of comparison table. One technique that was developed last couple of decades is super-resolution optical microscopy combined with a single molecule microscopy. This technique is based on attaching fluorescent label to a molecule of interest, and this label can be also a fluorescent protein embedded in a structure of the molecule that you would like to resolve. So optical microscope then excites electronic level of this protein or label, and you collect the photon emitted by this label, and that technique can be very, very sensitive. Nowadays, one can routinely observe single molecule even in a living cell. So there's a picture where the cell was labeled by several fluorescent proteins, and if you zoom in, you even can see single dots, single protein. So you can track single molecule, but you cannot watch inside of molecule. Always image a label. So it's not label free, and you can only image a label, not the biomolecule itself. Biomolecule itself usually don't fluoresce or fluoresce in deep UV or fluoresce weakly, too weak to be able to go to a single molecule level of detection. Nevertheless, so this is a very, very powerful technique, and with modern development in super-resolution microscopy like STED or PALM, you can reach a spatial resolution down to 10 nanometers, and you can do images with video rates. So the other technique that is routinely used is a nuclear magnetic resonance. So that's a very different technique, a very different path to image single biomolecules. When optical microscopy try to focus the light very tightly down to nanometer scale on a single molecule, NMR operates in a radio frequency range. So we're coming from an optical domain to a radio frequency. So the wavelengths of light in this case are many meters. And so if you would try to build a microscope that focuses microwaves, the diffraction limit would sort of pose you a border of meters. And so we are talking here about nanometers and angstrom. So the NMR is not focusing the radio frequency spectrum or radio frequency sort of spectrum part of light, but try to use a spectroscopic information to unravel the structure. So usually you take a spectrometer where atoms in a molecule resonates at certain radio frequency, and so measuring this response in radio frequency domain, so magnetic response, you can record very highly resolved spectrum of a complex molecule. So here the spectrum of a hydrogen region of the biomolecule, and so you see many, many lines. Each of these lines correspond to a hydrogen, but because of the interaction inside of complex proteins, interaction between atoms, these lines are slightly shifted. And this shift actually is carrying information about the three-dimensional structure of this protein. So by understanding basically this complex spectrum and putting some modeling in it, you can reconstruct the three-dimensional structure of such a complex protein molecule. And about the half of proteins that structure we know so far were unraveled using this technique. So it's a very powerful technique. So it can operate in liquids and ambient condition. You don't need to freeze the molecule, but you need the molecule to rotate very quickly in a solution. So it's not very easy to apply to a single protein, but maybe important limitation is the sensitivity. I will talk a bit later about this more, but usually you need billions and billions of copies of the molecules. So it's a very large amount needed to reach a signal-to-noise ratio to record this nicely resolved spectrum. So in improving the sensitivity of nuclear magnetic resonance, bringing this sensitivity down to a single molecule level, this is basically the main topic of the talk, to record NMR spectra of single molecule without averaging and being able to do it under ambient conditions and the conditions that molecule keep it function. So this is a big goal and big sort of a story of today's talk. So this is where our team is focused in, but also a few other teams around the world. Now, what is the sensitivity actually of magnetic resonance? That's why it's so limited. In magnetic resonance, we record magnetic response of molecules, spectrum of magnetic transition of nuclear spins, and those are lying in radio frequency domain. So it's not electrical, optical transition, so it's magnetic transitions, transition between magnetic levels, spin up and spin down. Those are separated in a magnetic field, and this separation, the energy of the transition, we would like to record with high spectral resolution. Technique is known for about 70 years now, and so the sensitivity was a limitation that was recognized from very early days from Erwin Hahn experiment. Actually, in NMR, you usually take your sample. That will be your molecule containing many atoms, hydrogen, carbon-13, and you excite these atoms with a coil. So you generate alternating magnetic field, and this radiation emitted by the coil get absorbed by the atom, and you record this absorption with the same coil, and this is kind of quite a noisy technique. This coil is a very noisy detection system, so you need a lot of atoms to get enough signal-to-noise ratio. This is one thing. So the coil itself is a noisy measurement instrument. It's used for 70 years. It's still a routine instrument to detect this magnetic spectra, but it is intrinsically noisy, especially at room temperature. Second point that limits the resolution is the low polarization of the sample. These magnetic transitions, so energy gap between spin up and spin down is not very high, even in very strong magnetic field. It's much smaller than KT. So sample essentially is widely unpolarized, so the number of spin down and spin up atoms is close to be the same. Just very small overshoot of spin up over spin down is bringing you the signal, and this is number at the room temperature is on the order of 10 to the minus 5 to 10 to the minus 6. So it means that out of 1 million of nuclear spin, only one contribute to the signal. Now you can ask yourself, can I do this something with a single molecule on this level? So in this situation you can. So because so to get the overshoot of one nuclear spin, so you need at least 1 million of nuclei, and molecule contain less nuclear spin. So the conventional technique based on a thermal polarization will never reach in this kind of approach the single molecule sensitivity. So new techniques are required, And these techniques are kind of under development. So, and especially on the side of a detection, quantum sensors provided a significant breakthrough. There are also other classical techniques, like, for example, using IFM, atomic force cantilevers, to measure forces induced by this nuclear spin is also a much more sensitive technique, and that's also under development. So it's not only quantum technologies that try to approach this problem, but we in Ulm and several other groups are trying to develop sensors that are based on a quantum properties of matter, of atoms, to make sensitive magnetometers to replace these coils. And this will be the topic of today's talk. In the very end, I will maybe touch a little bit the issue or the challenge of a low polarization of the sample. So here also quantum technologies can provide significant improvement. All right, so today's talk will be about making a magnetometers out of dopants in diamond, so NV center and diamond, and I will guide you through techniques enabling this magnetometry. Actually, it's a combination of EPR and NMR, electron paramagnetic resonance and nuclear magnetic resonance, and a very sensitive detection, optical detection of the color centers. So it's actually a combination of NMR, EPR, and single molecule spectroscopy that bring you sensitivity and spatial resolution. And what is also important for this field is basically ability to tailor diamond material to make these sensors. So this was basically initially a push in this field, enabling all this application and sensing. So what is the idea of making a better detection technique using diamonds? So we take a dopant in diamond, color center, that absorb and emit the light and use it as a magnetic needle, a compass needle. If you approach it close enough to a molecule, the nuclear spins that form, or the atoms that form a molecule have nuclear spins, and this nuclear spin induces a magnetic field at the location of your sensor. So if this distance is very small, the field is not negligible. So if you can come with your sensor very close to the molecule of interest, you gain twice. First of all, you can basically very locally address the molecule because the magnetic interaction fall with the distance. So if you can get very, very close, you have a very high spatial resolution and sensitivity, but also you get basically better signal-to-noise ratio because magnetic fields induced by atomic spins are stronger if you come very close. So you need very small sensor that you will be able to bring very close to the molecule of interest and measure magnetic field associated with this molecule. So the atoms that we use need to be then magnetically sensitive. And so we use optical transitions of color centers that have a response on the magnetic field. So by measuring fluorescence of this colored diamond, we basically get information about magnetic field of the molecule of interest. So why we use diamond for this technology? So diamond have several key advantages compared to other materials, although diamond is possibly not a unique material that is suitable for such a sensing technology. So diamond can be grown synthetically with very, very high purity. So nowadays there is a two techniques developed for growing a very pure diamond material. One is mimicking some of our natural diamond growth. It's a high pressure and high temperature technique. It's a reactor which you see here is an Element 6 company in UK reactor, bring the carbon to about 10 to 20 gigapascal pressure and temperature of about 2,000 degrees. That's what you have in the Earth, about 100 kilometer depth. And under this condition, graphite, stable form, so a diamond is a stable form of carbon, not a graphite. And so you can grow the crystals, very high purity. Even higher purity can be reached in a chemical vapor deposition technique where you grow a diamond on a seed crystal from a methane plasma. So in a plasma of methane, atoms can get kind of seated on a diamond surface, on a seed diamond surface, and this technique allows you to reach part per billion of beta purity level. So diamond will have now only carbon atom without any unwanted impurities on the level of purity 10 to the minus 9 or higher. In addition, we can construct the isotopic content of diamond by removing all magnetic isotopes of carbon, so making diamond only out of carbon-12. And in this case, inside of diamond, there is no nuclear spin, there is no electron spin, so it's very quiet magnetically. So it's what you want for making a sensor. You want your sensor don't have any intrinsic magnetic noise. So an ability to isotopically engineer the diamond, to remove magnetic atoms, allow you to make a sensor that looks like magnetic vacuum for you. Now, inside of this magnetic vacuum, we would like to put our sensors, our dopants that we control. But diamond is a unique material, take home that it can be grown very pure and can be grown from isotopes that don't have any nuclear spin. So diamond is a nice example in this case. So silicon carbide is another one. So maybe in a few years, we will also see development on a silicon carbide side, and groups here in Vilnius are working on a series of defects in silicon carbide and diamond. So I think that silicon carbide is also very important, but we work in diamond because we know this material quite well. So I show you a movie, actually, how this CVD technique works. This is a courtesy of my collaborator from Element 6, a daughter company of De Beers. So De Beers is not only selling natural diamond, but also growing synthetic diamond. And so they basically filmed this growth process in a chamber where you put a seed crystal. This crystal you should have at hand before, and now you switch on the plasma, and in a moment you will see how this diamond start to grow. So this is a moment where plasma is switched on. And so now you will see on this facet, so you see there's a layer of diamond rising. And so after some time, you can get a thickness of a millimeter. And the size of the crystal you get is given by the size of your seed crystal. So you can grow as large diamond as a seed diamond. And the composition of this diamond can be controlled very well by controlling the composition of plasma you use. So timescale is not as a commercial kind of a secret of the company, so I cannot share it. But I can only tell it's not a video rate. So it takes some time, and it's also so that the crystals that are grown in this way. If you keep the purity as a benchmark, also very expensive. So they wouldn't be competing even with natural diamonds because they usually are very expensive. But recently, this technique get basically developed so that some companies are bringing this diamond even on the market of jewelry. But so this is still takes some time to grow. All right, so the diamond itself is just a holder for our sensor. So it's magnetic vacuum, as I mentioned before, and now we want to introduce atoms that are sensitive to magnetic field, one by one. And the atom we are using since a few, maybe 20 years now, is a nitrogen vacancy color center. So it's a defect in diamonds that absorb and emit the light and give a color to a diamond when present in a high concentration. That's why it's called color center. So it's have energy levels within a band gap, and this particular center, NV, nitrogen vacancy, so name says about the structure, nitrogen and a carbon position and vacancy nearby. So this arrangement of dopants atom in diamond, or one dopant atom in a vacancy. Actually, in a solid state, vacancy is also something meaningful. So it has electrons in it, dangling bonds that are free. So this system has 6 electrons in total, and you can think about it as a molecule. So somehow trapped inside of diamond. So it has optical transition. It can be excited by light, and it can emit the light. And so this is this excitation and emission of light for this particular color center is flavored by the influence of magnetic field. So that's what we are basically using as a contrast mechanism for our sensor. So in order to understand this influence, I give you a brief introduction into energy levels. So the ground and excited state of these atoms are spin triplets. So they carry magnetic moment. They have spin sublevels, and optical excitation of this atom lead to emission that is now dependent whether you are in magnetic sublevels with magnetic quantum number 0 and plus minus 1. So these sublevels are emitting less photons than sublevels with magnetic quantum number 0. So by measuring emission, brightness of these color centers, you can tell something about magnetic field, because the separation between the sublevels is magnetic field dependent. Now the experiments we typically do, we do with engineered implanted color centers, and we visualize them in an optical microscope with single molecule microscopy technique. So what you see here is a picture of about 50 per 50 micrometer area or so, where dots represents implanted NV centers, engineered in well-defined location, and surrounding is very, very dark. So this deep blue color means no photons detected by your detector, and so this lightish color means higher photons detected. So this is an optical image where you see actually individual NV centers as bright dots. And this is like a very remarkable like picture of diamonds. So think about the purity actually what you have. There is in every dot here there is billions of carbon atoms, but there is no unwanted impurity. Only atoms that you introduced are lighting up, and they are now arranged in a kind of well-defined order. And emission of every of these atoms is dependent on magnetic field. So if you measure it carefully in the right way, you can say something about magnetic field. And now, because it's just one atom, so it's also a nanoscale sensor. The wave function of this color center is localized around the vacancy, so you have a second special resolution that is on the order of a few angstrom. Now, how we actually measure, so I mentioned before we measure photons. Yeah, we measure photons using a microscope objective, focus it on individual atoms. So objective has a waist of laser focus about 300 nanometers, but there is just one impurity atom laser focus. The rest is just carbon. They don't absorb, it don't emit the light, and so this the signal that we see is coming from individual color center. So we use quite a sensitive detection technique, but nothing special. So even commercial microscope from ZEISS or Leica can actually detect this color centers. You can buy even devices. We usually don't do because we don't like to spend such a lot of money for this. But if funding agency so can provide you with the funding, you can buy a microscope in a company. You can detect actually this picture in a commercial device. What is usually not yet implemented in a commercial device is microwave line to excite magnetic transition. That you have to put a small microwave antenna to excite this energy levels or induce transitions between energy levels of this NV center. We put usually some microwave line, and then we measure the brightness of individual spots as a function of applied microwave field. For NV center and a zero field, there is a strong resonance that you see here. You could detect the brightness, fluorescence versus applied microwave. and this resonance corresponds to transition between ground state spin sublevels. Now yeah. Well, we sometimes check whether just single color center or not, and that's we do by measuring G2 function correlation of light, and for this you need 2 detectors. The excitation of this transition lead you to change in population between bright and dark states. Remember, the states emit different number of photons, so if your microwave hits the transition, so it leads to a change of a total population of a bright state, so you can average over time, and then you get a response. If your microwave are hitting the resonance, you get more population in a dark state, the total fluorescence is less. If you're not hitting the resonance, most of the population is actually coming it's in a bright state, so you get higher fluorescence signal. So it's not an individual readout event. This picture was averaged basically many cycles, but it's give you a response, measurable response, about 30% difference in brightness. So if you have in a dark state, so your state is, your center fluoresces less, then you're in a bright state, and these resonances are quite narrow, actually. So for expert, the line width here is in this picture is in a megahertz, and for room temperature system, for room temperature EPR, that's quite a remarkable result. And in fact, using coherent control technique, we can bring this resonance line width even to smaller value. And the narrower its resonance, the more precise you can measure shift of this resonance in a magnetic field. So you get a sensitive magnetometer. So you can measure magnetic fields by measuring shift of the atomic transition. So and this is the basis of our sensing technique. So here's a picture how it looks like. I mentioned before, we typically build a microscope ourselves, and microscope is nothing else than a microscope objective lens and a sample placed somewhere here, and a holder that we are scanning. On the backside, there is electromagnet that tune a bit bias field to allow us to work at a transition at well-defined frequency at our wish. So this is a kind of a picture of the heart of this microscope, and we focus the green light on the sample somewhere here is a diamond and measure the red emitted light by the same objective. So this is a home-built confocal microscope. Now, zooming in, so this is how diamond look like. Again, there is a kind of a microwave antenna placed on top of diamond, and NV centers are implanted somewhere here near microwave wires. So the size of this diamond is about 3 × 3 millimeter, but the area near microwave antenna is just about 10 to 50 micrometers where we image NV centers. And now, so coherence comes in, so we also can create a coherent state, not only just excite magnetic transition, but also control precisely the state of this magnetic atom by applying resonant microwave field with well-defined duration. We can induce Rabi oscillation, so coherent dynamics of this spin. So this is a single NV center experiment. So if you apply right duration of microwave, you can inverse the population, so making a pi pulse in EPR terminology. Or if you apply shorter pulse, you create a coherent superposition between spin up and spin down. Now your atom is in kind of Schrödinger cat state, and at the same time have a spin up and spin down, and this state is very sensitive to external perturbation. You know, Schrödinger cat don't live very long because it's so sensitive. So usually any external perturbation projects it. So it's sensitive to external influences. And this quantum sensing technology is about measuring these influences by the action on a coherent state. So typically we excite this coherent state, spin up and spin down at the same time, and now leave the state to be influenced by external field and requires a phase. And experiments of this time, excitation and watching this phase is shown here as a function of time. So you see that the system oscillates, now oscillates on its own. And this oscillation frequency is related to external magnetic fields. So the more oscillation you can see, the most sensitive actually is your magnetometer. So the phase accumulation over a long time is more efficient. So for millisecond coherence time, so decay here is on a millisecond time scale, allow you to make a very sensitive magnetometer. So it's in general, for quantum sensors, the sensitivity is closely related to coherence time. The more coherent your sensor is, it means the more is isolated from unwanted noise, the better you can measure the signal you want to measure. So you want to have a long coherence of your sensor to reach a high sensitivity. That holds for a variety of sensors, from optical sensors, photons, to cold atoms, or to NV centers in diamonds. So the general frame that you have to increase your sensitivity. If you want to increase your sensitivity, you have to improve your coherence time. You want to look for a system with a long coherence times. And coherent state that lives for a long time allow you to acquire the phase associated with external perturbation. So NV center is sensitive to magnetic fields. So with this, you can make a very good magnetometer. Yeah, so this is a technique that we are using routinely now in many applications, and also other groups actually extended this magnetometry technique to a variety of problems in physics, in material science. Today I would like to talk about application of the sensors for measuring biomolecules. So remember, our goal we discussed in the beginning of the lecture to understand the structure and dynamics of single biomolecules by measuring magnetic field associated with single atoms, NMR, on a single molecule. And we are going to use the NV center as instead of the coil in NMR. So experiments I would like to show you was done a couple of years ago in collaboration with Harvard groups, Michael Lukin, Hong Kong Park, and Ron Walsford. And this is one of the first experiments where these NV centers were kind of tuned to detect biomolecules. So we took a piece of diamond and implanted NV center just about 2.1 nanometer below the diamond surface. Remember, it's very localized, so you can bring it very close to the interface. And on the top of diamond, so we put a protein that is not unknown molecule. So we took a very simple and robust protein, which structure was known as a ubiquitin, a regulatory protein, and connected it to the diamond surface. And then by measuring interaction between NV center and a protein, we're trying to get the information about the spectrum and the mass spectrum of this protein. So the approach actually seems to be easy, but it's always a challenge actually to connect the sensor to a biomolecules, and there is a lot of biochemistry involved. So actually the surface of diamond had to be functionalized with the groups that allow covalent binding of a protein, and it was done in the lab of Hong Kong Park that was using carboxy groups and then amino groups of the protein to connect. And so you see here the picture of a diamond surface made by atomic force microscope before getting protein on top and after connecting protein. You see the surface here is rough. The roughness is about a few nanometers, and this roughness is because of the monolayer of the protein sitting on a diamond surface. So it's close to a monolayer, very dense package of the protein, so it seems to be not compatible to a single molecule experiment. But there is just one NV center behind it, implanted just 2 nanometers below the diamond surface. And because of the locality of interaction, actually in NV center will only see one protein. The other proteins that are located more far apart will not be seen because the signal decays as a third power of the distance. So we coated the whole diamond surface with a monolayer of the protein, but having just one NV center allow you to reach a single molecule sensitivity. And here is a technique that was used. I mentioned that NV is a good magnetometer. It's also a good spectrum analyzer. So if you tune your microwave control and apply many pulses to the so many rotations to the spin of the NV center, you can tune it to a spectrally resolving device. So many pulses allow you to detect only one frequency of magnetic fields and refocus influence of other frequencies. And somehow similar to optical spectrometer, by making a grating, you allow the light to interfere constructively only in one direction. So basically tuning the distance between traces of grating and angle allow you to, in optical spectroscopy, allow you to do spectrum analysis, detect with your detector and a certain angle only one color of light. So here is the same, but in time domain, by placing pi pulses acting on your NV center spin at the right time separation, you allow you basically to make a spectrum analyzer, and now the phase that is accumulated by this color center is coming only for one particular AC magnetic field component at the frequency that is exactly matching the separation between pi pulses. So you can construct kind of a sensitivity function of your magnetic spectrum analyzer, and the sensitivity, so the resolution of the spectrum analyzer is given by the number of the pulses you apply. So similar to optical spectrometers, the more traces you have on your grating, the better will be spectral resolution. The same is here. It's just a spectrally resolving device if you want a grating in a time domain for magnetic field. So that's how we do. So we apply a lot of these pulses and now record again the fluorescence. So the fluorescence is the light emitted by this color center is carrying information about now the phase that is accumulated by the sensor. And so this is a picture of carbon and deuterium. This nuclear spin being introduced in the protein just to make sure that we detect right things, that we detect the protein is not some other molecules around. And those spectral lines that you see here, so this is a carbon and this is a deuterium, is a signal coming from a single molecule. Lines are noisy, as you see, so the signal to noise, it's not like in a spectra I was showing you before, but remember, this is the spectrum of a single molecule, a single protein containing just about a few hundred of atoms. And you need about a millimolar of molecules if you do conventional detection. So it's about 15 orders of magnitude improvement in sensitivity. So that was, I think, very significant this time, but didn't brought us to any new understanding of protein. We've been using protein that structure is known. And the big goal, again, is basically take a complex protein which structure is not known and understand the interaction between atoms to get the structure and make data acquisition fast enough to understand dynamics. So spectra you've seen before are too noisy yet to do it. They basically were recorded for an hour or so. And you want to, in order to see dynamics of the protein, you need to record the spectra every millisecond, at least a video rate every maybe 10 milliseconds. In order to resolve the interactions between atoms and reconstruct the structure, you need a very high spectral resolution. Actually, interaction between atoms, a J coupling, is on the order of a few hertz. And so we have had a few kilohertz here, so we also have to work on this side. So actually, two main challenges remains before the technique can be really applied to deliver useful information, not a demonstration, and that's improving the sensitivity to make data acquisition faster and improving the spectral resolution to make possible to resolve interaction between atoms inside of complex molecules. Right, and then if this would be possible, and here a lot of effort is now directed in many groups working with NV centers and other color centers, where it can go. So how you would think about experiments that you would like to do. So it's not like just, bringing protein covalently bound, maybe, which is a goal. So we would like to look on a membrane proteins. with unknown structure inside of cell. And so it can be done in two geometries. One is, which is maybe we think at the moment is easier to realize, is to take a piece of diamond and grow cells on it. Cell will have a membrane closely separated from the layer of NV center we create. And now, as an example, before we would now measure interaction between a membrane protein and NV center. So that basically would be continuation of the approach you have seen just before. So the other, maybe even more interesting possibility, but more difficult to do at the moment, is to take a piece of diamond, but of a nanometer size, and bring this diamond with NV center inside of the cell. So now you should be able to image now molecules inside of the cell, so not bringing the cell on top of big diamond, but bringing your sensor really to the place of a molecule you want to sense and measure magnetic fields there. So this approach is more difficult, and especially because it's much more difficult to reach a purity level I mentioned before for nanodiamonds, for diamond nanoparticles. But we are working on this, and several other groups are working on this to make a tailored diamond nanoparticle platform. And I'll just show you in the very end a few steps toward it. First of all, which diamond particles are available commercially. I mentioned before that a few university groups and companies were able to create very pure diamond material, but on a microscopic size. But what about nanodiamonds? So those are also available commercially, but they were developed so far mostly for polishing purpose, so they're not of high quality. So they are basically either created by milling larger crystal, Ph.D. also, but during the milling you introduce a lot of defects, including magnetic defects, so the powder looks dark afterwards, or by detonation actually. In a detonation conditions, you also get some high pressure and high temperature regime for a very short time. You also can create small crystals, but those are also have quite a lot of graphite, and in all of these cases, you don't know where your NV center is in this nanoparticle. So you don't have a tailoring positioning like we have had for the case of the bulk diamond. And so a few years ago, my colleague Phil Hemmer brought the idea basically to make a new type of synthesis that were not available so far. It's targeting creation of a tailored, well-defined diamond nanoparticle, having just one color center at well-defined location. And Phil's idea was to start with a seed molecule, adamantane, which is a molecule that resembles the structure of the diamond. So it has sp3 bonds, but it's too small. It's not diamond yet. It's not a solid state yet, but it's a chemically engineered molecule that have groups that you like to put, like, for example, nitrogen introduced in such adamantane. So this is possible to do by chemistry tools. But the size that chemists can do is only a few tens of atoms. So they cannot do chemical synthesis of a large diamond crystal, and even not a diamond nanocrystal. They only can do a few tens of atoms. But these seeds, a few tens of carbon atoms plus a nitrogen, can be synthesized. And now, so the idea was to put the seed molecule in a chamber where you will overgrow the seed. You will overgrow the seed and create a diamond. So the overgrowth mediums have to contain radicals that can get linked to the carbon atoms on the periphery of this seed molecule. So you want to have a seed, you want to have a growth medium, then overgrow the seed and get now a nanodiamond containing a few thousand or a few tens of thousands of carbon atom with a color center introduced in a well-defined location given by impurity atom placed by chemist during synthesis of seed molecule. Yeah? So it's basically make a diamond as well-defined as a molecule you usually have. So if you have a rhodamine or other fluorescent molecules, all of them are the same, up to a single atom. And so here it's about making nanoparticles with a similar degree of control. Well, it seems to be kind of a very direct path, but there are challenges. And challenges is that for overgrow, usually you want to have conditions where diamond is a stable phase of carbon. And in a phase diagram, that happens at very high temperatures and pressure. That's why you usually get diamonds growth under this condition, high pressure, high temperature. At these conditions, the seed molecule will decompose. So you might generate your seed molecule, put it into a reactor, make a synthesis, take out the diamonds, but during this process, the seed molecule will get destroyed. So you need to grow diamonds at very low temperature where seed molecules that chemists synthesized can survive. And this is basically a question whether this regime can be achieved. Actually, so far, the record, the lowest temperature that was used for growth is about 650 degrees by Davidov group in Russia, in Troitsk. And so we tried actually to push this limit down to a few hundreds of degrees where the seed molecules can survive. And so the way to do it actually is to control what's going on in the reaction chamber. So conventional HPHT process is a large reactor based. So this is a HPHT reactor in Japan, in Tsukuba, and you don't really have access to measure what is going on during the process. And so we would like to see whether seed molecule decompose or not. So instead of making this large machine that we might need later on for scaling up, but at the moment, so we work on a test of proof of concept. So we build a small diamond anvil cell, a small cell that allow you to go to high pressure and high temperature and control very well temperature and pressure in a very, very small volume. So the advantage of this anvil cell synthesis is actually optical access. You can excite material inside that you can detect the light. So you can also basically measure Raman spectra of the seed molecule during the synthesis and release of the pressure. And during this kind of conditions, we try to find a regime where the seed molecule does not decompose. So we worked on a few hundred degrees Celsius, and and first experiment showed that in V centers can be synthesized in such a nanocrystals, and we are still working on tailoring this process and checking whether all seed molecules survived and whether our color centers, we do have NV centers, but whether our color centers really originate from a location that was defined by chemists during the synthesis of the seed molecule. Right, and the vision of this again is to make a diamond nanoparticles of the very small size that can go inside of cell and sense proteins in vivo. So you can already now see a fluorescence of these NV centers. Those are red dots inside of the cells, but now we would like to make all the sensing scenarios possible, have NV centers with long coherence time very close to the surface to sense external biomolecules. All right, so I think that I will skip a few last slide and maybe come to a conclusion. So what we have seen that NV centers in diamond are remarkable magnetometers. And so today I was discussing its application for life sciences in nanoscale, like making sensors for biomolecules, NMR spectra of biomolecules, single biomolecules is possible to detect already. And nowadays, it's actually interesting that sensitivity of diamond-based technique is not limited to high magnetic field regime. So you can also have some interesting aspect of NMR spectroscopy of these molecules in zero field. So the sensitivity, if you measure the field, not the flux in a coil, is actually as good at low field as in high field. What I was not actually having time to discuss is application of NV center to polarize molecules. And actually, so this is also another interesting avenue and can have an application on a clinical MRI imaging. So not only sensing is possible with color center, but also polarization. So orienting spins with light. So if you do it on the sugars, and then the sugars are injected in the body, so they can be imaged in an MRI scanner with very high signal-to-noise ratio or with very high temporal resolution. So that's a very important approach. And last but not least, so all these techniques are somehow still bulky. So they cannot really be transferred to a biolab. And so basically there is a barrier. So that experiments are done mostly by physicists, but we're always talking that they have to be now transferred somewhere to some real world application. And I think here, like integration and simplification of this, so to make these devices more autonomous, user-friendly, is an important step. So there is also development in the field how to make the sensor smaller. So working on a push-button type of approach, and so we work together with a few companies. And actually, in the German Southwest, there is quite a number of industrial players that start to be interested themselves on this quantum sensing. One of them is a Bosch. So Bosch is known to be one of the biggest producers or developers of sensors. And so they also in their lab created an effort devoted to development of NV magnetometers, and recently have been able to build such a small sensor with a diamond inside it, all parts integrated. So what was before on a laser table size, so the experiments I was showing to you were on a room size, so they now can be put in a size of about a sugar cube. And so this is, I think, also important development, so that this quantum sensing protocol need to be taken at hand by engineers and made it small, user-friendly, and only then they can be really applied to some problems, in a biolab. All right, so with this, I think I conclude and would like to thank you for your attention, all the collaborations we had, and now our team at Institute of Quantum Optics in Ulm.
Thank you for a wonderful, exciting talk. And we're now open for some questions.
Thank you for the talk. How do carbon-13 isotopes influence measurements?
Sorry, I didn't get it.
Carbon-13?
Yeah.
Why do you have to remove it, and what would happen if you don't?
Yeah, so if you don't remove carbon-13, there will be a lot of carbon-13 signal coming from inside of diamond. And so that will somehow hinder your signal. So it might, especially if you want to sense carbon-13 inside of a protein. So they will basically, this signal will overlap with internal signal inside of diamond. So this is a reason. So if you want to study hydrogen, so it's less important to remove carbon.
More questions? Yes.
So in your single protein NMR spectra, the spectral resolution seemed to be still quite poor, but what was the limiting factor? It wasn't diffusion because it's attached to the diamond.
Right. Yeah, so spectral resolution in a spectra you have seen is an order of kilohertz. So there are two points that limit the spectral resolution. One is indeed diffusion of the molecule, but here molecule was sitting on a diamond, so it was not diffusing. And the second is the coherence time in this particular experiment of NV center. It's like, so the number of pi pulses you apply define how narrow is the filter function. And in this approach we have been using, so the number of pulses were defined by the total coherence time of NV, and that's about a millisecond at room temperature. So millisecond give you a kilohertz, so inverse of this as a spectral resolution. There are other approaches now developed in between that allow you to do much better spectral resolution, but in this experiments 2 years ago, so that was at the coherence time of NV center.
More questions? Yes.
So you mentioned that one of the goals is to make the measurements on like video speed. So what are the methods then you can like make these measurements faster?
So the speed of the measurements is basically, it means how long I should acquire for one kind of frame. And so this is basically, sensitivity. So the more sensitive is your sensors, the more measurements you can do in a unit of time. Now, the sensitivity in quantum sensing is related to coherence time. So there is no way to improve sensitivity without improving coherence time or making more atoms contributing to a signal. So you need either more measurements or more copies of your sensors. But so there are two ways to improve it. So having more NV centers contributing to a signal is sort of difficult because you want to remain nanoscale. So you could think about making billions and billions of NV centers. It will be more sensitive, but then will be large. So you will not be able to get a signal from a single molecule in this case. And so the only way to improve the sensitivity is to increase the coherence time. So if you would increase the coherence time to like 100 milliseconds or so, then you will be much more sensitive. So that's one thing. Or if you have a limited sensitivity at hand, bring your NV center closer. So if this NV center was about 3 nanometers below the diamond surface, and so if you would be at 1.5 nanometers, the magnetic fields from a molecule is much stronger. And so then you can average much less and make more measurements. So I would say it's a combination of two. So like new techniques, new microwave pulse sequences that allow you to keep coherence for longer time, better material perhaps, better surfaces, but especially also maybe trying to bring NV center even closer to the surface.
All right, I'm afraid we have to stop here. Take your chance to catch Fedor in the breaks and ask all the questions there. Thanks a lot, Fedor. Let's give him a hand again.